Hi, my name is Tomer, and today we're going to talk about attenuation of early reflections in television studios using pre-trained speech synthesis neural network. So let's talk about acoustic reflections. When a microphone captures a single sound source in a room, the acquired signal consists of the direct sound and the acoustic reflections. While the reverberations, which arrive later than 50 milliseconds after the direct sound, cause adverse effect to sound quality, the early reflections that arrive in the first 50 milliseconds are traditionally considered as something good that boosts colorations and intelligibility of sound. But in the setup of television studios and sound monitoring applications, they actually cause adverse effect to the sound quality. Now, most of the solutions proposed to reduce those early reflections in studios are related to the room properties, such as the geometry and materials and the proposed design methodologies. Now, these solutions are effective but expensive. In this work, we propose a method based on machine learning that can be implemented in any arbitrary studio design and doesn't require a new design. Now, we assume a model of in a discrete time domain. The clean speech is considered as X, and we assume that the observed signal is a linear convolution between the ground truth signal and the room impulse response, H, and we acquire in the microphone the signal Y. Now, the only thing we assume about the room impulse response H is that it doesn't contain late reverberations, only early reflection, meaning that the T60 values of this H is shorter than 50 milliseconds. And our goal is to design a neural network-based model F, such that if we feed the observed signal Y to this network, we get estimation of the clean signal without the early reflections. Now, we observe that those early reflections are very noticeable in the spectrum and in the short time Fourier transform magnitude. For example, if we take a signal with only one single reflection 2 milliseconds after the direct sound, we can see notches in certain frequencies. Since it's so noticeable in the short time Fourier transform magnitude, we think that convolutional neural network is a natural choice to remove them. So our proposed method consists of two stages. It accepts as input waveform and produces a waveform in time domain. The first module is F. It's a unit-based neural network. We consider it as the attenuation module. It accepts the short time Fourier transform magnitude and produces a new magnitude without the reflections. Then this magnitude is transformed to MEL domain, and the MEL magnitude is fed to G, which is a speech synthesis neural network, which reconstruct from it the waveform time domain signal. Now, it's important to mention that F is the only trainable module in the system, and G is kept fixed during all training. Now, in order to train the module F, we need to synthesize some room impulse responses. So we generate this room impulse responses in a synthetic way. It consists of two terms. The delta is corresponding to the direct sound, and the second term corresponds to the early reflection, and they are generated in a random way. The exponent term ensures that the T60 value of this HT is according to the chosen T60. BT enforces the room impulse response to be sparse, and NT is actually just to make those reflection random. And then given a clean speech signal X, we generate H and the corresponding corrupted signal Y. We train the module F to minimize this loss. It contains two terms of spectral loss between the short time Fourier transform magnitudes between the ground truth signal X and the output of F. The second term is between the ground truth signal X and the output of G. Now, this spectral loss also consists two terms. The first term is L1 loss between the short time Fourier magnitudes, and the second term is the L1 loss between the logarithm of those magnitudes. Now, to validate the performance of our proposed system, we compare between four baselines. The first baseline is the degraded, it's just the original corrupted signal Y with early reflections without any processing. The baseline F is just we take the output of F, the magnitude, and reconstruct the time domain waveform using the original phase of Y. The baseline G, we take the original signal Y, we don't use F, we transform it to mesh domain, and then reconstruct it using G. And F plus G is our proposed full system. Now, to evaluate the performance, we also need an estimation of the room impulse response. We estimate it using least square estimation with L1 regularization. Here, X is the Toplitz's matrix corresponding to the clean ground truth signal X. H is the impulse response, and Y is the baseline, meaning one of those four baseline. The L1 regularization enforces the output to be sparse as we expect it to be sparse, as this is how we generated H. We also compute the clarity index, C2, which measures the ratio between the energy in the first 2 milliseconds after the direct sound over the energy in the rest of the room impulse response. Larger value for C2 means better performance. So here is the visualization of the estimated room impulse response for the different baselines. As can be seen, the best performance is for F plus G. As we can see that the room impulse response is very close to delta and there are not so much reflections compared to the other baselines. For the clarity index estimation, we generate a lot of room impulse responses and validate the performance, and we show it as a function of the T60 value. Now, as can be seen, F plus G achieves the largest clarity index. An interesting thing is that the output of F is almost constant with respect to as a function of T60, while the other baselines decrease in performance when the T60 value increases. We also attach the DNS MOS rating, which are predictions of the human mean opinion score as a subjective evaluation. As can be seen, F plus G achieves the highest DNS MOS ratings. And for last, we also show visualizations of spectrograms of the different baselines. As can be seen, this is the spectrogram of clean ground truth signal. This is a spectrogram of the degraded signal. We can observe the notches. As can be seen, the output of F plus G is very similar to the output of the clean signal. An interesting thing about G is that it helps to attenuate the notches that are in the high frequency bins, but not so much in the low frequency bins. This result actually makes sense because when we use G, we transform the signal to melt domain and we lose information about the high frequency bins of the short-time Fourier transform magnitude. And then the Hi-Fi gun reconstruct them from scratch. So that's it. For future works, we plan to first extend the setup to the multi-channel signals, like in a microphone array, as we assume that we can take leverage of spatial information to improve the performance of the algorithm. Also, we want to extend it to a full bandwidth in a sampling rate of 48 kilohertz, since in practice, those solutions are meant for television studio where high-end studio quality is required. And also we considered of conducting a test using a professional soundman to evaluate the performance and so that's it. Our plan for future work is first to extend this work to the multi-channel setup, since if the signal is acquired by a microphone array, we can use spatial information for better performance. We also would like to extend it to a full bandwidth sampling rate of 48 kilohertz, since we consider the problem of television studios when high-end quality is required. Another interesting direction for future work is conducting a test using a professional soundman, help them to let them evaluate the performance of different methods, and maybe use those ratings to as an objective term for that is correlated with subjective subjective evaluation of speech. That's it. Thank you very much.